So can somebody tell me what were the transformations that we had done in example 2 before the video was done? Yes. Okay. What else? Yes. Okay. And then one more? Yes. Left one. Okay. So we're going to go ahead and we're going to take the points that we have for an absolute value graph, and we're going to do those 3 transformations on the points so that we can graph this function by hand. Okay? So what are the points that we use for absolute value graphs? You can flip your notes over and look at the example 1. Okay. And how did I get those points? Did I just make them up, or do they come from something? They come from the parent function. So I used x values, -2, -1, 0, 1, and 2. I used those x values, and then I was able to get the y coordinates by plugging them into the parent function. The parent function is just y equals the absolute value of x. So I got them by plugging them into the original graph with no transformations, just to see what they are. Now I'm just going to go through and I'm going to apply the transformations to see what this transformed graph would look like. And when we do the transformations, we still have to think about, please excuse my dear Aunt Sally, so we're still thinking of order of operations. And we're going to think about transformations that include multiplying or dividing have to happen before transformations that include adding and subtracting. Which basically means if you go from left to right, you'll be fine. Okay? So we're going to do reflect over x, and we're going to do vertical compression first, and then we're going to do the left one. Because reflect over x and vertical compression, those have to do with multiplying, and shifting left one has to do with adding or subtracting. Okay, so that's the order we're going to do it. All right, so if you reflect over x, you're taking something that might be above and you're reflecting it, so it's going to be below. So something up here goes down here. So is that a y coordinate change or is that an x coordinate change? That's a y coordinate change. So you're taking your y coordinates and what are you doing to them? Flipping the sign, or you're taking the y coordinate and you're multiplying it by -1. Okay? If you're doing a vertical compression of 1/2, you're taking something that was this tall and you're compressing it so it's half as tall. So if you're taking something and you're making it so it's half as tall, what are you doing to it? You're compressing it, but think in terms of the numbers. Is that going to happen to x or is that going to happen to y? That's going to be y again, right? Because that's an up and down shift, or an up and down change, not a left and right change, okay? So if I take something that is 10 feet tall and I compress it 1/2, how tall is it now? 5. If I take something that's 26 feet tall and I compress it 1/2, what is it now? 13. So what are you guys doing to those numbers? If I take something that is 20 feet tall and compress it by 1/2, what is it now? 10. So what are we doing to those numbers? We're dividing them by 2, we're splitting them in half. Okay, so how could we take something, we said this is a change to the y value, reflecting over x changes the y value. Vertical compression by 1/2 also changes the y value. So we said reflecting over x changes the y value, it changes the sign, it's like multiplying it by -1. A vertical compression takes the number and splits it in half. Could we do both of those things at the same time? How would we do it? Multiply by -1/2, which makes sense because that's what you have in the front. Does that make sense? Okay. So what we're going to do is we're going to take the y coordinate and multiply by a negative to be able to do the reflection, and multiply by a 1/2 to do the compression. Okay? So I'm going to keep the x values the same. Keep the -2, -1, 0, 1, and 2. Those are all staying the same. And then we're going to take the 2 and we're going to multiply it by -1/2. What's 2 times -1/2? -1. Okay? 1 times -1/2. -1/2. 0 times -1/2. 0. 1 times -1/2. -1/2. Okay, and then 2 times -1/2. -1. Okay, now since these are our notes, we should be writing down what we've done. So we multiply by -1 for the reflection, and we multiply by 1/2 for vertical compression. So altogether we multiply by -1/2. We did that to the y coordinate. Okay. All right. How do you feel? Tired? Does it make sense to your brain? Your brain feels comfortable? Yeah, that's good. Okay, the next transformation we have is we're going to take the points and we're going to shift them to the left 1. Is that going to change the x coordinate or is that going to change the y coordinate? It's going to change the x coordinate. So if you take the coordinate and you shift it to the left 1, it's going to change the x coordinate. What are you going to do to the x coordinate? You're going to subtract 1 from it. Okay, so let's take all the x coordinates and we're going to subtract 1 from them. So -1, -1, -1, -1, -1. Okay? And there was no up or down shift, so there's no reason to change the y values again. So now we can just write our y coordinates, copy those down. I'm gonna write what I did here, so subtract 1 from x for left 1. Okay. Now we have done all 3 transformations, and this is the result over here. And so this is what we're going to graph. This is the final answer. Okay, so we took the original points from the parent function. We did all 3 transformations on the points. And so once we've done all 3 transformations, that means that we have the transformed graph. We just have to graph it. Okay, so -3, -1, left 3 down 1. -2, -1/2, -1, 0, 0, -1/2, 1, -1. Okay. And you can see the graph has been reflected over the x-axis. You can tell because it's upside down. You can tell that it has been vertically compressed by 1/2 because it's not as tall as they normally are. It looks a little bit squished. And you can tell that it's been shifted to the left because normally the vertex is in the middle and it's a little bit off-centered. Okay. All right. We feel pretty good about that? Okay. Go ahead and write down the transformations that you see for example 3. There are 2 of them. 2 transformations. Zoe, I'm so sorry. There's a whole stack of papers there. I apologize. You were so patient about it. You're like, she'll notice eventually and she'll move on. All right, what do we think? Transformations. We see. Anybody? Just shout it out. Vertical stretch of 4, okay. And down 5. All right. Okay, so let's write the points. We've got negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. So how do we do a vertical stretch of 4? Yeah, take the y coordinate, multiply it by 4. So instead of it being 2 tall, it's going to be 4 times as tall. It's going to be 8 tall. Instead of being 5 tall, it's going to be 20 tall. So we want to take however tall it was to begin with, we want it to be stretched so it's 4 times as tall as what's normal. So we're going to take the y coordinate and multiply it by 4. So I'm going to keep all my x coordinates the same. And then I'm going to take my y coordinates and multiply them by 4. So 2 should become 8. And 1 should become 4. And 0 should become 0. Okay. And then the next transformation is down 5. So how do we do a shift of down 5? Subtract 5 from the y coordinate. Okay, so we're keeping the x coordinates the same. And then we're going to take each of our y coordinates and we're going to subtract 5. Okay. So once we've done that, then that column is our graph. So left 2, up 3, left 1, down 1, 0, negative 5, 1, negative 1, 2, 3. Okay, now be careful. Should this be a solid line? No, because this is an inequality. Y is greater than. So this is a dotted line. So we're going to draw a dotted line. I hate it when the points are this far apart. I feel like I cannot draw a straight line. So dotted. So this is not like the linear functions where you have like a left side of the line and a right side of the line, and you would just shade on the left or shade on the right. This is one where you have an inside versus an outside, okay? So if we plug in the point 0, 0, then that would be considered the inside of the V. So we're going to say, okay, the inside of the V is either true or false, and then the outside of the V is either true or false. Does that make sense? So we're not going to say up versus down or left versus right. We're going to say inside versus outside. Okay? So let's pick 0, 0 because we're lazy and it's easy to plug in. So 0, 0 is on the inside. And then we're going to say 0 is greater than 4 times the absolute value of 0 minus 5. Does anyone remember what the absolute value sign does to a number that's inside of it? It removes whatever negative sign could be in there with it. Okay, 0 doesn't have a negative sign, so it didn't remove anything. So what I'm going to do is I'm just going to take this problem and rewrite it with a parenthesis there, because there was no negative sign to get rid of. So it's just 4 times 0. So what is 4 times 0? 0, okay. So we have 0 is greater than 0 minus 5, which is just negative 5.
Yeah, the vertex is 0, negative. So the vertex is 0, negative 5. And because it's a, shift down 5, so horizontal position. And then the shading is above the line because it's greater than. Maybe it was just like what I just noticed self-explanatory, sorry.
So saying the shading is above the line because it's greater than is not an absolute statement. Well, that doesn't always work.
Since y is just by itself.
It doesn't always work. So that might work in some situations when equations are set up certain ways, but it does not always work that way. Which is why, so I'm not going to teach you shortcuts that don't work all the time. Because then students will pick up on that and say, oh, well, this worked this time, so I'm just going to always use that, and it doesn't always work. So what does always work, though, is plugging a point in and seeing if it's true or false, because that's literally how the math works. So I'm going to teach you that method. Now, does that work in this situation? Possibly. Does that work in every situation? No. So if you were to take this, if something was in standard form, it would stop working. But not obviously. Okay. All right, so 0 is greater than negative 5. Is that true or false? True. So because 0 is on the inside of the absolute value symbol, or the absolute value graph, we're going to say the inside is true, because that's where we found a point that was true. That means that the outside, where the points were outside, that these would be false areas. So anything inside should be true, anything outside should be false. Does that make sense? Okay, so that means we're going to be shading inside. Okay. All right, so we have two things that we're going to work on for the remainder of the period. We're going to be practicing the transformations, and then as we go through Math 3, we're going to be studying absolute value graphs. We're also going to be reviewing quadratics, which you guys learned about in Math 2. We're going to be reviewing square root functions, which you learned about in Math 2. We're going to review a little bit, we're going to look into cubic functions, x to the third. We're going to look at cube root functions, square root of, or the cube root. And then we're going to be looking at all other types of functions. So we're taking what you guys did in Math 2, and we're just getting deeper into all those functions, okay? So transformations are a part of that. We're going to do transformations, what we just learned, we're going to do that for all of the functions that we learn about this semester. So the stuff that you just learned, we're going to do that same process with those transformations and the charts. We're going to do that for every function that we learn about this semester, which is like, I don't know, like 6 or 7 different functions, okay? So you want to make sure, I started you guys off on the easiest one, okay? It does not get easier than absolute value functions because that V shape is basically a straight line and a straight line, okay? So I started you off as easy as we could. They're going to get complicated, okay? So if you have questions, you make sure that you ask them today, because the next one is a little bit more complicated because it will align with this more. Does that make sense? Okay. Now we're transformations, but we're going to look at what characteristics or keys of the graph. So you did this in Math 2, like increase and decrease goals, or the graph positive and negative. Some that probably made you uncomfortable. What happened is in Math 3, you can't be comfortable by because with angle unit 6, we're going to find those things, and we want a point where we these questions get to like the 5th unit. Those are easy questions. That's why I give means on the test because you're going to get all those. Sense. Today is kind of a vocabulary day is our introduced. So again, I'm off on the E because it's been a straight line, and the line they make off on the E introduce vocabulary. That means this isn't where it's important to have. Starting at E, not forget stuff. Not just get into transformations. I didn't run, so I'm going to do for this. I divide the test. It's not like that. We're doing it. Go ahead and hand out. You've talked about these words already, maybe in Math 1, definitely in Math 2. The next 2 words we're going to remember, but we're going to use a lot in Math 3 are domain and range. Okay? So domain is all of the x values, which are the inputs that are defined in a function. This means that you can plug a value into the function and get an answer. So domain is all of the x values that are the inputs that are defined in a function. It means that you can plug a value into the function and actually get an answer out of the function. Okay? The range is all of the y values or outputs that are defined in the function. Basically, this is the answer that you get after you plug an x value in. Do you guys like my blanks? This long blank for the word in?
Yeah.
Plug an x value in. Plug an x value in. In. Okay, good. All right, so here are 2 examples, specifically in the context of the unit that we are talking about, okay? So typically when we talk about the domain, we say, what are the x values that we can plug in? And when we look at this, we think about, okay, absolute value means I'm plugging in an x value, and then I'm taking that answer and I'm forcing it to become positive. Is there any limit to the amount of numbers you have that you can force to become positive? Are there any rules about numbers where it's like, yeah, you can make this number positive, but not this one? We've never heard about any rules like that, right? And so we would say that the domain is all real numbers, okay? The other way that you can see it on the graph is you can see that the arrow goes left, which implies that this graph is going to left forever, so it has all the negative values, so all the negative x values, and the arrow is going right, so the graph is going to the right forever. So you can find the domain by looking at the x values on the graph, or you can find the domain by thinking about what you would plug into the function, okay? So we would say if you cover up the picture of the graph and you look at the equation and you ask the question, what x values can I plug in? That's you thinking about the domain algebraically. So when I ask you the question, what x values can you make positive? That's me saying, okay, that's what absolute value means. And so I'm thinking about the domain algebraically. And then when I look at the picture of the graph and I say, oh, this graph goes forever to the left and forever to the right, and it doesn't skip any numbers, that's me finding the domain graphically. Does that make sense? So when I look at it both ways, I can say like, oh, the domain, it doesn't skip anything. There's no X value that I wouldn't be able to plug in. So my answer for domain is all real numbers, which is that funky looking R, all real numbers. Or if you like the interval notation, you can say negative infinity to positive infinity. And because we are dealing with that V shape, that is going to be true for every single graph this entire unit that looks like a V. Always all real numbers, always negative infinity to positive infinity. Okay? So I'm going to write that for example 1. I'm going to write that answer for example 2. Yeah, people call it double bar R. So you're writing a capital R, but you write it with 2 lines. Double bar R. All right. Now the outputs, on the other hand, the range, these are going to be somewhat limited, okay? Because you can see it's harder to tell algebraically, like if I covered this up and asked you what the range was, you'd be like, I don't know. But if you look at the picture, you can tell it pretty easily, and that's very common with the range. Usually you cannot tell what the range is from the equation itself. Typically you have to look at the graph to be able to tell. So if we look at the graph, we can see that the graph goes down forever, all right? But we can see that the graph does not go up forever, it stops, okay? And the graph stops at a y value of 2. Everyone see that? Stops at a y value of 2. So we would say that the range is y is less than or equal to 2. Y is less than or equal to 2, okay? So that's one way to write it. You should not be on your laptop right now. Nope. Okay? Or the other way to write it is you could say your down arrow is your lowest number. So you'd say negative infinity is your lowest number. Your highest number is a 2, and you would put a bracket. So infinity is like a number that you're not including. Infinity is like an idea. I can't really put my finger on infinity. Like I can see that it goes down forever. But if you said, hey, Miss Rice, show me where it hits negative infinity, I'd be like, I cannot touch that. That would be like right here, I'm putting my finger on infinity, but I'm actually touching negative 6. I can't actually touch negative infinity. But if you say, hey, Miss Rice, touch 2, I'd be like, 2, it's right there. I can actually touch that one, so I put a bracket there if I can actually touch it. Okay? So negative infinity is the bottom, 2 is the top. Okay, the next one, this one does not go down forever this time. It stops at the bottom, it stops at negative 7, but it goes up forever. So for this one, we would say y is greater than or equal to negative 7. Or if we were to write it in the interval notation, we would say negative 7 is the bottom, and positive infinity is the top. We would put a bracket around the negative 7 because we can touch it. We would put a parenthesis around the infinity because we cannot touch that. Yeah. So you always go from down to up because you do your smaller number first. So even though negative infinity feels like a big number, it's actually not. It's the tiniest number you can imagine because it's negative. So it's a very tiny number. It's big negative. It's big tiny. So here, negative 7 is small. Infinity is huge. So we're going from down to up. We're going from smallest to biggest. Does that make sense? Yeah. So down to up. So smallest to biggest. Good question. All right. The next thing we're going to look for is the vertex, which some of you guys already mentioned, being able to find just from looking at the equation. The vertex is the point where the graph switches from increasing to decreasing. or vice versa. So we think about this as where the graph switches from slanting down to slanting up, or from slanting up to slanting down. We often think of this as the middle of the graph, or we might think of it as the starting point of the graph. A lot of us think of it that way. Some graphs don't have a vertex, but there's a point that seems kind of similar to that in nature. We call this the locator point. So we will study some functions later on that don't have a vertex, like a square root graph does not have a vertex, but it does have a point that's kind of similar to that idea. A cube root graph, say it again? Yeah, so like a cube root graph goes like this. So technically it doesn't have a vertex because a vertex has to be where it switches from increasing to decreasing, and a cube root graph would only be increasing, or it would only be decreasing. So the definition doesn't fit what a vertex is, but it does have a middle. It has like that middle point that we typically find, and so in that case I just call it the locator point. It's that like special point that we look for. The vertex and the locator point are found in the equation using h and k. And the vertex or locator point is written as the coordinates h, k. Don't turn the page yet. Don't turn the page yet. We're actually going to go back up to example 1 and 2. And we're going to write the vertex for these two problems. So the vertex for problem 1, you always have to do the opposite of the number for the h. So for example 1, the h would be positive 3, not negative 3. So the vertex would be positive 3 and then positive 2. So for the vertex, you do the opposite sign of that number that's inside, just like you do the opposite of whatever's in the inside for the transformations. So that minus 3 tells you that it shifted to the right 3, and it tells you that the vertex is positive 3. Okay, so what would the vertex be for example 2? You can just say it. Negative 4, negative 7, perfect. Okay, so we're going to pause right there in our notes, and we're going to go ahead and start working on the assignment. So at this point, if you look over at the assignment, we can definitely do problems 1, 2, and 3. They ask us to write the transformations. They ask us to write the vertex. We can definitely sketch the graph without a calculator. We can use the table to kind of sketch the graph. We can find the vertex for 4, 5, 6, and 7. We can definitely do 8 through 13, where we are taking the graphs that are already drawn and matching them with their equations. We can do 14, where we have something, an inequality that's graphed already, and we have to write an equation for it. So we can probably, at this point, we're to the point where we could do 1 through 20, really. So I'm just going to give you guys some time to work, and then we might do some more notes this period, we might not, okay? So, but the plan is that throughout the next few days, we're going to get to the point where we do finish all these notes, but it might be just a little bit at a time each day so that we don't feel too overwhelmed as we learn this new vocabulary, okay? All right, so at this point, our goal is just to do 1 through 20. We'll see how far we get. Sound good? Okay.